Alright, I know what you're thinking. Andy, why the heck do you make a video about math? Your other videos are about you playing video games. Well, that's because I can do whatever I want, dude. I'm the video maker here. But to be truthful, I made this for my brother because he's going to university soon for the same program as me, and I know how difficult my first year was. And then I figured, I might as well put this on the internet, since a bunch of people are going to university at this time, and maybe in the same situation as my brother, but they're not completely sure what to expect. Well, I won't waste any more of your time. Let's get started. So what is discrete math? Well, if you took data management in your high school, or whatever the probability course in your high school was, you probably have a decent head start. To my knowledge, this course deals with a lot of different topics. Probability, like I've just mentioned, but also things like combinatorics, and worst of all, proofs. Don't worry about what they all mean at the moment. Remember, I am here to try to show you guys what you are getting into. I am not qualified to teach you guys everything about the subject. There's a bunch of videos on YouTube already for that. I am going to give you an example for combinatorics, probability, and proofs in this video. Let's start with combinatorics first, because that's what I learned about first in my experience. Remember, you can pause the video whenever if something does not make sense. I find that if one part of the math doesn't make sense, the rest of it won't either, so don't be afraid to just take a moment to process the information that I give you. Alright, so combinatorics. It is pretty much the math of counting. If that sounds simple, well, let me explain the steps first. Combinatorics is an attempt to figure out how many ways there are to obtain an outcome, at least in my understanding. There are two questions to ask when attempting an accounting problem. Does order matter? And is there repetition? Order mattering just means the objects, when arranged differently, results in a different outcome. Repetition means that an object can be used in the outcome multiple times. If that doesn't make sense, let's try an example. Imagine you're at a donut store, and you want 12 donuts. The cashier tells you they have 4 flavors. Naturally, you wonder, how many unique ways can we pick 12 donuts if there are 4 flavors to choose from? If you thought, Andy, how the fuck am I supposed to think about this in my head? You are correct. It is rather difficult to think about, and that is why old mathematicians came up with an easier way to do it, by drawing it. For now, don't worry about the actual answer. Just focus on what I'm about to show you. This is called a stars and bars question. Let's use the flavors chocolate, sprinkle, old-fashioned, and vanilla. In this picture, the stars represent the donuts, and the bars separate the flavor sections. This is one way to pick the donuts, but we can also move the stars around to pick a different amount of each flavor. I believe you can tell at this point that at different arrangements of stars and bars, they represent different ways to pick 12 donuts with 4 flavors. Now try to figure out how many ways we can order these stars and bars. Pause and ask yourself, does order matter? And is there repetition? Alright, the answer is that order does matter, since, well, you can see that moving these stars and bars around gives a different set of 12 donuts. And repetition is also allowed, since we repeatedly use stars and bars to generate different sets of 12 donuts. Congratulations. Now, I could show you the formula used to calculate the actual total ways to get 12 donuts with 4 flavors, but I don't really want to overload you guys with information. Just know that once you've answered the 2 questions, you pretty much plug in the numbers into a formula and boom, you did it. Alright, if you're still with me, nice. You have enough attention span to do one university level math question. Let's move on to the probability. Now maybe you're thinking, Andy, I did probability in high school. It's easy. Okay, smarty pants. Let's try this example out. This example is called the Monty Hall problem. You may have heard of it. Here are 3 doors. There are 2 goats and 1 chicken jockey popcorn bucket signed by Jack Black. Naturally, you want the popcorn bucket. However, I stop you before you go for it and put the items behind the doors. Then I ask you to pick a door, maybe you choose the left one, and then I open one other door, showing you a goat, and ask if you want to switch doors. Now you are thinking, oh, then there's a 50-50 chance of getting the chicken jockey no matter the door, right? Wrong! Alright, let's take a step back. Let's say all the doors are closed, and you decide to pick the left door again. Okay, then we make a statement about this decision. The odds that you successfully pick the chicken jockey is 1/3, while the odds that you unsuccessfully end up with a goat is 2/3. Now, I open a door, showing a goat, and ask if you want to switch to the other closed door. Let's consider the following. There's a higher probability that you picked a goat. And when I reveal one of the two goats, because there's a higher probability you picked a goat, it is always better to switch doors. Because there is always a higher probability that the chicken jockey is behind the other door that you did not select. If you think I'm spreading misinformation, give it a Google search. Let's move on to the last topic I'm covering, proofs.
This is fine.
Proofs are quite possibly the worst types of mathematical problems I've had the misfortune of learning about. I actually think these are a torture method designed by the ancient math people, strategically portrayed as harmless educational math questions. But whatever. Here's an example of a discrete math proof. Let's try to prove that the expression n to the power of 3 minus n is divisible by 3, assuming that n is a natural number greater than or equal to 1. This is done by something called an induction proof. First we start with something called a base case, which is the smallest possible case of this statement. This would be the number 1, because we're using natural numbers starting from 1. Subbing 1 into this expression, 1 to the power of 3 minus 1 is 0, and 0 divided by 3 is 0, and this base case fulfills the condition of being divisible by 3. Now, we move on to the induction hypothesis. We suppose that for any natural k greater than or equal to 1, basically saying for any natural number, this statement is fulfilled. I'm serious, we just suppose this. It doesn't matter what the variable is. Afterwards, we have the induction step, where we try to prove that k plus 1 fulfills this condition. So we just plus k plus 1 to the expression, and expand out like so. After you take a look at the entire calculation, please take a look at the last line. The term on the right is divisible by 3, because it's being multiplied by 3 already. But what about the left? Well, if you remember the induction hypothesis, we already supposed this expression is divisible by 3. So therefore, this entire expression is divisible by 3, prove the induction step, which is the last step. Since we have shown that both the base case and the induction step hold, using the induction hypothesis, we have proven that the expression n to the power of 3 minus n is divisible by 3. I apologize if any of that was confusing. Go ahead and review this example a couple of times if it doesn't make sense. Try to think of it like this. The base case is to prove that a statement is true for the easiest value. The induction hypothesis is to assume that statement is true for any random value. And the induction step is to show that the statement is true for the immediate next value of that random value we just picked. This effectively proves the statement is true for all values we were considering, because the base case is like a sanity check, and the induction hypothesis and step show that the statement is true for any random value we can pick. Okay, that was the last example. I hope I managed to enlighten you guys. Maybe you still have no idea what I just talked about, but that's okay. If you guys are just a little more concerned about going to university, then I'm going to consider my job here done. But if you're not, well, that's okay too. Personally, I didn't really prepare for university when I was a high schooler either. I just kind of winged it. But that did mean my first year was very shocking to me. But I'm still hanging in there, so maybe that means you guys can hang in there too. The way I like to think of university is that it makes you feel completely terrible, so that nothing in the rest of your life will feel as terrible. In my opinion, this is the case no matter what kind of program you're in. It's a test of mental willpower, basically. But whether you thought the math in this video was difficult or not, please remember, no matter how difficult it gets, or how much you feel like giving up, if you keep moving forward, there is always a non-zero probability of things getting better. Stay safe, everyone. Thanks for watching.